No? Okay. The next thing we want to look at is how does more samples, how does including many samples rather than a single sample reduce error, right? We have observed that if we use more samples, we get less errors, okay? And the question is exactly how less does more samples lead to? Okay, so first of all, this is something we can do both experimentally and analytically. Experimentally, that's something we can easily observe that here's the rule of thumb. If you use 4 times as many samples, you are expected to reduce the standard error by a factor of 2. If you use 100 times as many samples, you are expected to reduce the error by a factor of 10. In other words, the error behaves like 1 over square root of the number of samples. Okay, so that's a pretty slow convergence, and theoretically, we can actually prove that. We can prove that based on a single assumption, is that if you use additional samples, the additional samples you are going to be using are independent from the first set of samples. So let's try that analytically. We're just performing the estimation of the expectation of x. Instead of using a single sample, now we are using 2 samples, x1 plus x2, divided by 2, right? So that's going to be our new estimator, our improved estimator. Now the question is, how does that reduce the number of samples we require? Okay. In this case, my estimator is actually x1 plus x2 divided by 2. So this is basically saying that now I'm going to be treating the all the collection of possible samples I get when I perform my first sample as a random variable. That's going to be my x1. All the possible samples I'm going to get when I sample my second sample is going to be another random variable, x2. This is important because x1 and x2 are not the same random variable. Because if they are the same random variable, that means my first sample would always be equal to the second sample, which is of course not the case, right? I sample twice, I get 2 different numbers almost surely. So x1 and x2, they are samples of the same distribution, which means they are so-called identically distributed. So x1 and x2 are identically distributed. But they are also independent, right? Which means how x1 varies has nothing to do with the distribution of x2. So another way to say that is, if I give you the value of x1, right? If I already performed a sample of x1, but without performing a sample of x2, my knowledge of what x2 can be would not change if you tell me something about x1. That statement is called independent. So x1 and x2 are not just identically distributed, but they are independent. And identically distributed. In probability theory, the concept of independent and identically distributed is so important that the people have a shorthand for that. That's called IID. So independent, identically distributed random variables. This is commonly what we get when we sample something multiple times. Okay. And independent basically means if you give me some knowledge about one, it's not going to increase my knowledge about the other variable. All right. Identically distributed just means they have the same distribution if you perform it multiple times. So let's keep going. This is our estimator, and the thing to be estimated is still the expectation of x, right? So expectation of x is the thing we estimate, which is equal to the expectation of x1, which is equal to the expectation of x2. Now, our standard error is equal to the expectation of, well, half of x1 plus x2, that's our estimator, minus expectation of x, right? That thing is square root. Now let's try to figure out how does this standard error relate to the standard error we calculated previously, which is the standard deviation of x. Okay, so let's try that. The first task is we are going to be just splitting this whole thing into half times x1 minus expectation of x1, because x1 has the same expectation as x and x2, plus x2 minus the expectation of x2, right? So it's basically the average of the two differences, expectation and square root. Sorry, expectation of this, sorry, the standard deviation has a square inside the expectation. So it's actually expectation of this squared, and after the expectation, I have a, what is it? Is there a question? No? Okay, yeah. So this square is within the expectation, and this square root is outside the expectation. All right. So this term and this term are independent. And it's interesting that in statistics, in probability theory, there is a very important rule or theorem we should be using. That is, if there is two random variables, let's call them U and V are independent, then expectation of U times V is going to be equal to the expectation of U times expectation of V. I mean, this is basically saying that U and V has no interaction, right? So the expectation of the product is equal to the product of the expectations. Used in our particular case, it's actually pretty important because we have a square, and whenever you factor out x plus y squared, there is a term of 2x times 1, right? And the 2x times y, in this case, we have a one-term x here and the y here. So we have a term that is the expectation of product of two independent random variables, right? Because x1 is independent of x2, and these are just the numbers, right? So if you formulate a function of a random variable, it's also independent from another function of an independent random variable. So, okay,